Welcome to another module in this massive open online course on estimation for wireless communication systems. In the previous module, we have looked at the Cramer bound, which provides a fundamental lower bound on the variance of an unbiased estimator, right? We have derived an expression for the Cramer lower bound, which characterizes the lowest possible variance that can be achieved by an estimator. Alright. So, now in this module, let us try to look at an example to understand this computation of the Cramer-Rao lower bound better. So, let us look at an example in the context of a wireless communication system to compute the Cramer-Rao lower bound. Alright. So, in this module, let us look at an example wireless scenario to compute the Cramer-Rao lower bound, which we also simply called as the Cramer-Rao bound or basically the CRB. So, example wireless scenario to compute the Cramer-Rao bound. Yeah, and let us go back to our wireless sensor network scenario. Let me remind you, we have already considered our wireless sensor network scenario. In which we have a sensor node. So, this is our sensor and which is trying to estimate a parameter h. This is the unknown parameter to be estimated, and we have made n measurements y1, y2 up to yn. These we have called our n observations or n measurements. So, we are considering our wireless sensor network scenario where there is a sensor node which has made n observations y1, y2, yn of the parameter h to be estimated, and each observation yk is given as the parameter h plus the noise Vk, that is the parameter h being observed in additive white Gaussian noise. So, we have Yk equals h plus Vk, where Vk is additive white Gaussian noise. Additive white Gaussian noise. In fact, we have also derived the likelihood function for this. It is nothing but the joint density of the observations y1, y2, yn, that is denoted by the observation vector y bar. So, we have the likelihood function, and you can also recall that this likelihood function, which is the joint density of the observations viewed as a function of the unknown parameter, that is 1 over 2 pi sigma square. So, let me light it a little bit clearly, that is the likelihood function p of y bar characterized by the parameter h is 1 over 2 pi sigma square raised to the power of n by 2 times e raised to minus 1 over 2 sigma square summation k equals 1 to n yk minus h whole square. What is this? This is your likelihood function of the likelihood function corresponding to the parameter h, which we said we have derived from the probability density of the observations y1, y2, yn, which is denoted by the vector y bar viewed, that is the probability density function when we view it as a function of the unknown parameter h. This is the likelihood function. Alright. So, now to compute the Cramer-Rao bound or the Cramer-Rao lower bound, I have to first start by basically computing the Fisher information, that is I of h. That is what we said about the Cramer-Rao lower bound. Remember, the Cramer-Rao lower bound corresponding to the parameter h is given as expected h hat minus h whole square is greater than or equal to 1 over the expected value of the square of the derivative of the log likelihood function, yeah, and this quantity here, that is the expected value of the square of the derivative of the log likelihood function, this is nothing but your Fisher information. This is basically the Fisher information corresponding to the parameter h, and we also said the higher the Fisher information, the larger the Fisher information. The larger the Fisher information, the more information the likelihood function conveys about the parameter h, hence the lower is the mean squared error. Naturally, if the information is more, the error is going to be lower, and that is an interesting property, or that is an interesting intuition from the Cramer-Rao bound. Alright, so to do that, to compute the Fisher information, we start by computing first the log likelihood function from the likelihood function, and then the derivative of the log likelihood function. So we have an expression for the likelihood function, that is what we have already seen. Now let us compute the log likelihood function, the natural logarithm of the likelihood function. This is your log likelihood function. And this is, we have also derived the log likelihood function n by 2 log 2 pi sigma square, in fact minus n by 2 log 2 pi sigma square minus 1 over 2 sigma square summation k equals 1 to n y k minus h whole square. This is your log likelihood function. Now, if I compute the derivative of the log likelihood function, you can see that the derivative of the log likelihood function with respect to the parameter h. Now, you can see this part is a constant, this does not depend, that is this minus n by 2 log of 2 pi sigma square, this does not depend on h. So, that the derivative of that with respect to h is 0. So, what I am left with is minus 1 over 2 sigma square summation k equals 1 to n, the derivative of basically your y k minus h whole square, which is minus 2 times y k minus h, the negative sign because there is a negative in front of the h, and therefore, this can be simplified as the derivative of the log likelihood function is basically 1 over the 2's cancel. So, this is 1 over sigma square k equals 1 to n y k minus h. So, we have computed the log likelihood function, from that we have computed the derivative of the log likelihood function, and we can see that the derivative of the log likelihood function is 1 over sigma square summation k equals 1 to n y k minus h. And we already know that y k equals h plus v k, where v k is the noise. So, y k minus h is nothing but v k, that is the noise. So, we know basically now if you realize, and that is also very clear, let me repeat that y k equals h plus v k implies y k minus h is nothing but basically v k, which is the noise. This implies the derivative of the log likelihood function p of y bar h with respect to h equals 1 over sigma square, instead of y k minus h, simply replace that by your quantity v k, and this is basically the derivative of your log likelihood function, that is 1 over sigma square summation k equals 1 to n summation Vk, that is the derivative of the log likelihood function. Now, the Fisher information is the expected value of the square of the derivative of the log likelihood function. So, let us now compute the Fisher information, which is the next step to evaluate the Cramer-Rao lower bound. The Fisher information is the expected value of the square of the derivative of the log likelihood function, that is y bar h, the square of the derivative of the log likelihood function, which is the expected value of, basically we computed the derivative of the log likelihood function, that is 1 over sigma square summation k equals 1 to n Vk whole square. Now, 1 over sigma square is a constant, so that will come out of the expectation. So, that is basically 1 over sigma square square, that is 1 over sigma 4, 1 over sigma raised to the power of 4, expected value of summation k equals 1 to n Vk whole square. Yeah, so that is 1 over sigma raised to the power of 4, expected value of summation k equal to 1 to n Vk whole square. Now, this I can also write as basically your 1 over sigma to the power of 4 expected value of summation Vk whole square. I can write it as summation k equals 1 to n Vk times itself, but I am going to change the index, and this is a trick that we have seen several times before. K tilde equals 1 to n Vk tilde, and now if I expand this product of two summations, I have expected value of summation k equals 1 to n summation k equals 1 to n Vk tilde. And now, since the expectation operator is linear, I can move the expectation operator inside, and what I have is basically 1 over sigma raised to the power of 4 summation k equals 1 to n summation k tilde equals 1 to n expected value of Vk tilde. And this is something that we have seen several times before, that is expected value of Vk tilde. Remember, we have said the noise is white Gaussian, additive white Gaussian, and also we have said basically that means that the noise samples, another way to say that is basically the noise samples are independent, identically distributed Gaussian random variables, right. So, these noise samples Vk tilde, these are IID Gaussian, all right, and we have explored the properties of these noise samples in detail many times earlier. The IID Gaussian, which means they are identical Gaussian, which means each of them has mean 0, that is Gaussian with mean 0 and variance sigma square denoted by n 0 comma sigma square, and they are independent, which means basically the expected value of Vk into Vk tilde is basically equal to 0 if k is not equal to k tilde and is equal to sigma square if k equal to k tilde. So, let me just summarize that once again, so that you can just quickly recollect this property. Since they are independent, we have expected value of Vk tilde is basically equal to sigma square if k equals k tilde and 0 if k not equal to k tilde, which basically means that expected value of Vk tilde is basically sigma square delta, that is the discrete delta k minus k tilde, right. Sigma square delta k minus k tilde is basically sigma square if k equals k tilde and 0 if k is not equal to k tilde. I am going to now substitute this expression for the correlation, that is expected value of Vk tilde in basically the expression for I of h, that is the Fisher information of the parameter h that we have derived above. So, therefore, we have I of h equals basically your expected value of the square of the derivative of the log likelihood function which is basically 1 over sigma 4 summation k equals 1 to n summation k tilde equals 1 to n expected value of Vk tilde, and we have just seen that this is basically sigma square delta of k minus k tilde, which means this is equal to 1 over sigma raised to the power of 4 k equals 1 to n k tilde equals 1 to n k tilde equals 1 to n sigma square delta k minus k tilde, which means in the summation k tilde equals 1 to n, only the term corresponding to each k tilde equals k will survive. So, this is basically 1 over sigma to the power of 4 k equals 1 to n sigma square for each k tilde equals k, which is basically n times sigma square. Summation k equals 1 to n sigma square is n times sigma square divided by your sigma raised to the power of 4. So, this is equal to n, this is equal to, this is nothing but n divided by sigma square, and this is a very interesting result. What we have just established is that the Fisher information for this sensor network scenario is n divided by sigma square. And what is this? This is basically your Fisher information. Fisher information of the parameter H. So, for this wireless sensor network example that we have seen several times before, in fact, one of the first example that we have seen in the context of maximum likelihood estimation. So, we have now demonstrated or derived an expression for the Fisher information of the parameter H, and we have demonstrated that this Fisher information denoted by I of H is equal to n divided by sigma square, where n is the number of observations, sigma square is the variance of each of the IID Gaussian noise samples, and also this Fisher information is basically nothing but the expected value or the average value of the square of the derivative of the log likelihood function of the parameter H. Okay. And now computing the Cramer-Rao bound is simple. The Cramer-Rao bound is simply the inverse of the Fisher information, that is 1 over I of H. Therefore, now the Cramer-Rao bound, that is your Cramer-Rao bound is basically equal to 1 over the Fisher information, which is basically 1 over n divided by sigma square, which is basically equal to sigma square divided by n. This is the Cramer-Rao bound. This is your CRB, which means is the lowest variance achievable by any unbiased estimator, and therefore, we have the Cramer-Rao bound, which is basically expressed as expected value of h hat minus h whole square is greater than or equal to sigma square divided by n, and this is basically the Cramer-Rao bound for the sensor network scenario. This is your CRB this is the Cramer-Rao bound for the sensor network or the wireless sensor network. So, we are saying we have derived the Cramer-Rao bound, which is the minimum variance achievable by any unbiased estimator, and that we have demonstrated is equal to sigma square divided by n. So, the variance of any estimator which yields an unbiased estimate of the parameter H has to be necessarily greater than or equal to this quantity sigma square by n, which is the Cramer-Rao bound. And you will notice something very interesting, that we already have an estimator which achieves this Cramer-Rao bound, and that is nothing but the maximum likelihood estimate. If you recall, for our maximum likelihood estimate, H hat equals 1 over n summation k equals 1 to n, summation k equals 1 to n of y of k. This is basically what is this? This is basically your maximum likelihood estimate for the wireless sensor network. This is basically the maximum likelihood estimate for the wireless sensor network, and the variance of the maximum likelihood estimate, variance of this maximum likelihood estimate is in fact, you will be happy to recall, variance of your maximum likelihood estimate, that is expected value of H hat minus H whole square, is in fact sigma square divided by n. Yeah. So, what is interesting, that is, not only have we demonstrated through this Cramer-Rao bound approach that the lowest variance achievable is sigma square divided by n, we already have an estimator in fact which achieves this Cramer-Rao bound, that is in fact the maximum likelihood estimate, which is also the sample mean of the observations, that is 1 over n summation k equal to 1 to n y of k. This is the sample mean of the observations y1, y2 up to yn. We said this is a maximum likelihood estimate which is derived by maximizing the likelihood of maximizing the likelihood function with respect to the parameter h, and this estimate, the maximum likelihood estimate, already achieves this lowest variance, that is sigma square divided by n. So, the maximum likelihood estimate achieves the Cramer-Rao bound, and therefore, there cannot be any other unbiased estimator which has a lower variance than the maximum likelihood estimator. So, the maximum likelihood estimator indeed turns out to be the best suited estimator for this scenario. So, the maximum so to summarize, basically our maximum likelihood estimator, our ML estimator achieves the CRB which is equal to sigma square by n. Therefore, ML estimate has the ML estimate, which is also abbreviated as MLE, has the lowest MLE, or basically the ML estimator has the lowest variance for any unbiased estimator, and such an estimator is said to be basically efficient. Any estimator which achieves the Cramer-Rao lower bound is said to be an efficient estimator, implies that it achieves the Cramer-Rao lower bound, that is, it gives the lowest possible variance. In this case, that is also the mean squared error. Since it is also an unbiased estimator, the variance is also basically your mean squared error. Yeah. So, basically what we have demonstrated in this module, as we have taken a concrete example considering a wireless sensor network scenario with n observations, we have derived the Fisher information, the likelihood, the log likelihood, and from that basically the Fisher information. From the inverse of the Fisher information, we have derived the Cramer-Rao lower bound for parameter estimation in this wireless sensor network. We have demonstrated that this Cramer-Rao bound is basically given by sigma square divided by n, which is the lowest variance achievable by any unbiased estimator of the parameter h. And not only that, interestingly, the maximum likelihood estimate, the simplistic seeming maximum likelihood estimate, but yet which is very powerful, that we have derived earlier, also achieves this Cramer bound, which means it has the lowest variance amongst the class of all unbiased estimators. Therefore, there cannot be any other unbiased estimator which has a lower variance, which means that the ML estimator is the best estimator for this estimation scenario, and also therefore, this is also known as an efficient estimator since it achieves the Cramer lower bound. We will stop this module here and explore other aspects in subsequent modules. Thank you very much.